Dear friends, in the series of learning gas turbine technology, so in this class we are going to discuss how to obtain the that means gas turbine cycle efficiency, because Brayton cycle efficiency and also we can obtain, but that means this simple gas turbine cycle works on the Brayton cycle. But when we are deriving the expression for the efficiency, especially for the Brayton cycle, so Brayton cycle efficiency will be using only the heat supplied and heat rejection. So but whereas in the case of simple gas turbine cycle, that means so we are what we are going to do, we are going to take the turbine work and compressor work into account. So based on that we are going to derive the expression for the efficiency. So this is the main difference between the Brayton cycle, that means Brayton cycle efficiency and simple gas turbine efficiency. Because Brayton cycle we are just considering only the heat supplied and heat rejection, whereas in simple gas turbine cycle we are considering the turbine work and compressor work and also the heat supplied. So now let us see the diagram. Okay, so we all know that this is the simple gas turbine engine, so that means open gas turbine engine. So for that we have the PV diagram, pressure volume diagram. So and in this pressure volume diagram we all know, okay, so where the heat supplied and this. So this is the heat, we can just say Q, okay, heat supplied, and here heat rejection. So so this is by using heat supplied and heat rejection only we used to derive the Brayton cycle efficiency. So whereas in the case of gas turbine we are going to consider the turbine work as well as compressor work. So that is what, okay, the turbine work and compressor work and also heat supplied. So we have written, okay, based on the input condition and output condition. That means this input output refers based on the numbers what we are denoting here. So that means compressor work is based on T2, that means 1 to 2. That means in the process 1 to 2 that we are taking. That's why Cp T2 minus T1. Then similarly turbine work nothing but T3 minus T4. So it is between the points 3 and 4. Then heat supplied, okay, that is due to the combustion where fuel is added. So that is between the, that means 3 and 2. That is what T3 minus T2. So okay, this is what we are going to use it for deriving the gas turbine, that means gas turbine cycle efficiency. So then net work output, we are using net work output nothing but turbine work minus compressor work. So this is nothing but, okay, so the efficiency formula, okay, so efficiency formula nothing but turbine work net work divided by heat supplied. And yeah, so this is a TS diagram. So okay, we will be discussing more about TS diagram in the upcoming classes. So right now, okay, that is just a symbol, okay, for the simple gas turbine cycle, how the TS diagram looks. So because this is we are showing it as the dotted line because it is the open gas turbine engine. So because of that we are just showing as the dotted line. So we will discuss more about TS diagram in the upcoming classes. So now let us derive the expression for the gas turbine cycle by using the turbine work and compressor work. So okay, I hope, okay, this point these equations are clear. Okay, that means how we are just writing the all the, that means enthalpy change. It is based on the enthalpy change we are writing the equation of the turbine work and compressor work. So and also the heat supplied. So okay, so now let's work further to get the efficiency formula. Okay, so now first thing is first we have to write down the expression, that is adiabatic rule. So based on the adiabatic rule or based on the adiabatic conditions, we know. So based on so adiabatic rule, we can just say. So this is because the 1 to 2 and 3 to 4 both are isentropic compression and isentropic expansion. So for the isentropic compression, we can write T2 by T1, T2 by T2 by T1 equal to P2 by P1 whole power gamma minus 1 by gamma. Okay, so this is for the isentropic compression, and then yeah, this is for then we can just say for process 1 to 2. This is for process 1 to 2. So then for the we can similarly we can write for process 3 to 4. So that is nothing but T3 by T4, T3 by T4 equal to P3 by P4. So yeah, so this is gamma minus 1 by gamma. So this is for the process 3 4. Okay, so this is okay. So now we got the expression based on the adiabatic expression, that means reverse adiabatic rule or adiabatic law. So for the reversible adiabatic reversible adiabatic process, so or isentropic process, we are writing that means T2 by T1 equal to P2 by P1 whole power gamma minus 1, and similarly for the isentropic expansion. Okay. Now this is we all know, that means in the case of P3 is nothing but P2. So because it is a constant pressure heat addition, so since we know P3 equal to P2, then P4 equal to P1. So this is okay, we have to make a note of it. So this is we have seen in our previous Bratton cycle efficiency also. So this is okay, this we have to use it here. So when we are using it here, and this equation becomes now let us yeah, erase this. This equation becomes now T3 by yes, so T3 by T4 equal to now because P3 equal to P2, P4 equal to P1, so it becomes P2 by P1 whole power gamma minus 1 by gamma. Then this we are going to take it as the C, that means P2 by P1 nothing but we can just say RP, pressure ratio. So P2 by P1 nothing but pressure ratio, that is gamma minus 1 by gamma. So this expression RP power gamma minus 1, that we are going to consider as the C. So let us take this as the C. Then we are going to take one more assumption, that is nothing but T3 by T1, T3 by T1, so that is equal to T. So nothing but it is the maximum temperature okay to the minimum temperature. So this we can say as the temperature ratio, and this is okay based on the pressure ratio, that and raised to the power gamma minus 1 by gamma. So that we are taking as C. Okay, so by using T and C, we are going to simplify our previous expression. Let us this erase this. So our efficiency, we know that W net is nothing but we have seen. So W net is nothing but, so that is the turbine work minus compressor work. So we have seen Cp into turbine work, okay, T4, that means T3 minus T4 minus Cp into yeah, T2 minus T1. So this is, yes. So this one we are going to simplify. We are going to take Cp into T1 outside. That means in the whole expression. So that means here we are writing T3 by T1 minus T4 by T1 minus T2 by T1 minus, okay, minus into minus it becomes plus. So this is okay. So now we got this expression. This we need to simplify further. So that means we are going to use these two. So we have taken the assumption, that means Rp power, that means T3 by T4 equal to this P2 by P1, because this is also equal to, we know this is we also equal to yeah, we can just say T2 by T1, T2 by T1 equal to this T3 by T4, that is what, okay, equal to P2 by P1 whole power gamma minus 1 by gamma. So this is for this we can take C, and T3 by T1 we can take T. Let us take, that means particularly we are C denotes this one. So if you say this, that is equivalent to this, that means to represent this we are using T1, that means C. Now this simplify this further. So that means okay, so this is equal to Cp into T1 into T3 by T1, nothing but because we have taken T3 by T1 as the T, that means T3 by T1 only we have taken as T. So that T minus this is T4 by T1 that we are writing in now, okay, expressing in terms of T4 by T3 into T4, that means T3 by T1, T3 by T1 minus T2, so we just say T2 by T1 plus 1. Okay, so that means now what happened, we are going to replace this T4 by T3, T4 by T3 nothing but 1 by C. So this is okay, because T3 by T4 is C, so T4 by T3 is nothing but this one we can replace as the this one we are replacing as 1 by C, yes, 1 by C. Then this one T3 by T1 is nothing but T, so this one we can replace as the T. Then as usual T2 by T1 nothing but yeah, T2 by T1 nothing but C, so this is nothing but C. So now C, yeah, this is nothing but C. Okay, so we got, okay, so that means we have simplified that all the temperature ratios has been written in terms of T and C. So this is what further we have to simplify, that means we can write this is equal to Cp into T1. So we are just taking T minus C, T minus C minus, so just we can take it as T by C minus 1. So we are taking like this. So yeah, whole. So this is T minus C minus, we are taking minus outside, minus into minus plus. So okay, this is one expression, that means this is what W net. So W net equal to Cp into T1, this T minus C minus T by C minus 1. Okay, now let's go for the equation that efficiency. So the efficiency can be expressed, okay. So the efficiency we are expressing in this, okay, equation. So efficiency equal to W net by Qs. So this is equal to W net we have seen Cp into T1, then T minus C, minus, that means this we can write T minus C by C, okay, so then whole divided by C, that means Q heat supplied, so that is nothing but Cp into T3 minus T2, T3 minus T2. So this one okay, we are going to simplify. So this one it has to be simplified. So that means from here we are going to take the T1 outside. T1 we are going to write it. So I am just going to this one nothing but Cp into Cp into T1. So that means then inside what we have to do, just we are dividing both T1. Okay, so since we are that T1, okay, we are multiplying, then here we are dividing T1 T1. Okay, so then it means this CPT1 gets cancelled. So here both gets cancelled, then remaining, so that we have to write. So the efficiency now equal to T minus C minus this is okay, T minus C by C whole divided by T3 minus T3 by T1, nothing but T, then T2 minus T1, nothing but C. Okay, so now we can cancel out this whole, okay, in this numerator and denominator we can cancel out this, so this and this. So now the remaining, that resultant becomes efficiency equal to 1 minus, so because denominator is okay 1 only, so 1 minus 1 by C. So we know what is C. C is nothing but 1 minus C is nothing but C only we have taken as the this 1 by RP, that means pressure ratio power gamma minus 1 by gamma. Okay, so this is the expression. Even we got it for the Brayton cycle efficiency. So this is okay, very important. So even for the simple gas turbine cycle, by taking the turbine work and compressor work, we are getting the same expression as that of Brayton cycle efficiency. So that we need to note down, that is very important. So even though that method of obtaining this deriving this expression is okay in a different way, but finally we are getting the same expression as that of Brayton cycle efficiency. Also one more thing we have to note down, this Brayton cycle efficiency depends on, that means gas turbine cycle efficiency, also the Brayton cycle efficiency, both depends on pressure ratio, because that we have to write, both depends on this efficiency, we can just say depends on, so two things, so depends on, so just we can say as the one is nothing but pressure ratio, then next one pressure ratio nothing but RP, then next one specific heat ratio, that is a gamma. So here that 2 you can write specific heat ratio gamma, nothing but gamma. Okay, so I hope this